Can you hear me now? I hope.
Yeah.
Okay, good. So I will also talk about collapse models, and I hope I will convey you some further information with respect to what Giancarlo already told you. So I want to show you this model from a different perspective. You know the motivation, Giancarlo already said, it's a measurement problem in quantum mechanics. The idea is that somehow, we are at the non-relativistic level. You buy the quantum formalism, you buy the idea that the wave function, in a way, is directly connected to reality, to individual physical systems, but then you have the problem with the superposition principle, which has been tested at the microscopic level, but then it's not part of our daily experience, in spite of the fact that the theory easily predicts the existence of microscopic superpositions. And so the idea to solve this situation is to modify the Schrödinger equation by adding nonlinear and stochastic terms. So in a way, if you want to use the words of John Bell, you assume that the collapse of the wave function does not occur only at the end of a measurement process, but more or less every time, more or less everywhere, more or less for every physical system. So it's a property of nature. It's not something peculiar of a measurement situation. And so in this way, you have a unique dynamics which describes in a consistent unitary way both the quantum properties of microscopic systems and the classical property of macroscopic objects. And in fact, the title of the original GRW paper was a unified dynamics for macro systems, something more or less like that. Okay, I will not spend much time. You have some relevant literature on this topic. So as I said, I want to take a slightly different perspective. So suppose that we are back in the 80s, there was no GRW model, and then you pose the problem, how can I modify the Schrödinger equation in order to solve the measurement problem? So historically, it has been done by trial and error till GRW found a solution, but let's ask the question in more general terms. And actually, over the years, this has been asked by several people, and perhaps the one that, in my taste at least, was able to focus on the real physical motivation was Steve Adler, who suggested and somehow argued that the requirement of no fast and light signaling, of course, if you also include norm conservation, but that's clear, uniquely identifies the class of post-modifications of the Schrödinger equation. And that class happens to coincide with that given by collapse models. I want briefly to give you the mathematical proof of that. So that goes back to the work of Gizen, but also, as Giancarlo said, it was further elaborated by himself with Renata Grassi. Take the usual situation of Alice and Bob playing with entangled pairs. So they have two particles, one going to the left, one going to the right. Alice can do any type of measurement she wants. Then, in a way or another, whether at the fundamental level or at the practical level, you have the collapse of the wave function. That's the way you describe consistently outcome of measurements. So when Alice measures something, then she reduces the wave function also on Bob's side, and she reduces it to an ensemble of states. And the important property is that by changing the type of measurement, Alice can generate different ensembles, which are, however, equivalent, so they are described by the same density matrix. But now suppose that Bob waits for some time after Alice's measurements and waits for the dynamics to change the state of the system. And let's suppose that this dynamics is not the one given by the Schrödinger equation, but is the one that you're looking for, the modified dynamics which describes the measurement process. Well, then you can easily understand that if this dynamics does not preserve the equivalence among density matrices, then you can easily devise a protocol for superluminal communication. And that's Gizen's argument. So the conclusion is that whatever dynamics we are looking for, this must preserve the equivalence relation among statistical ensembles. Or, from the mathematical point of view, it must be a well-defined and linear evolution for the density matrix. So that's the conclusion of Gizen's paper. Of course, the question is, what's the form of the equation for the wave function which leads to a linear evolution for the density matrix? And so now I come to, so to the experimental part of the talk, or phenomenological one. These models modify the Schrödinger equation, so they make predictions which differ from standard quantum predictions, so it's interesting to see whether you can test them. And there are possible ways to test them. Of course, the most straightforward way of doing that is to perform a double-slit experiment, or in more modern terms, a matter wave interferometry. These models go against the superposition principle, so the most direct way is to test superpositions. I will not say much because I suppose that Marcus after me will extensively talk about that. So I just want to comment that how nice is to see that with the technology, the size of the system of the molecules which have been used for the experiment constantly increases. And so far, these experiments place a bound which is 2 orders of magnitude away from Adler's suggestion, which is the strong value for lambda. So some 10 orders of magnitude away from GRW value. So, so far, they are very close to testing these models, and if, as Marcus promises, in the near future they will be able to reach the size of molecules of 10 to the 6 atomic mass units, then they will become crucial tests of the collapse models, at least with respect to the value of Adler. I just briefly mentioned that people also are doing other type of experiments with micro mirrors and cantilevers, nanospheres, and there is the idea in the far future even to do experiments in outer space in order to overcome technological difficulties when doing experiments here on Earth. Okay, that's enough with matter wave. Spontaneous photon emission. Here, this is an indirect test of collapse models and therefore of the superposition principle. Take a charged particle. According to quantum mechanics, nothing really interesting happens. But according to collapse models, this particle interacts with the noise. It is shaken and pushed here and there. It's accelerated, it's charged, and therefore it emits radiation. So you have the prediction of spontaneous emission radiation by particles, by free particles, but also by particles bounded in matter. And then so you do an experiment, you place a detector in front of a piece of matter and you see where the radiation comes out. No one really did a dedicated experiment, but still there is some experimental data which is available, rough data which you can use. And you get 3 messages out of that, which are quite relevant. The first one is that you need to introduce the mass proportionality in the GRW or the CSL model, otherwise these are ruled out by experimental data. This is not surprising, and people would have done that independently of these experiments, because for the very simple reason that since the collapse rate scales with the size of the system for compounded systems, then you would naturally think that a proton, which is 1,000 times more massive than an electron, suffers a collapse in a stronger way than an electron. It's a very natural within the philosophy of collapse models. And moreover, this points towards the gravitational origin of the collapse process. But nevertheless, even if you assume the mass proportionality in the collapse models, the comparison of the theoretical prediction of, more specifically of the mass proportional CSL model with the experimental data would exclude Adler's value for lambda. It's too strong, so it's violated by experimental data. But then, if you do the analysis in a careful way, you realize that the theoretical prediction very much depends on the correlation function of the noise. So if the noise is white, then you have a violation with experimental data. But a white noise is a mathematical idealization. If this noise has any physical origin, it must be a spectrum. It must have a spectrum with a cutoff. And if you take into account the possibility of a cutoff, a very reasonable one, not a weird one, then you easily restore compatibility among the theoretical prediction and the experimental data. But you see, it's interesting to point out that experimental data already starts to say something about collapse models, and it already starts to exclude at least the most naive ideas. Then you can play with energy non-conservation. Energy is not conserved in these models for a very simple reason. They interact with this noise. The noise pumps energy into the system, and the equations don't say that the system gives the energy back to the noise. And so you have energy non-conservation. Of course, the energy non-conservation is very tiny, completely negligible for any type of experiment done on the Earth. But then you can try to look at big systems like the universe or cosmic structures in the universe and see how this affects the evolution of these structures and how observational data put a constraint on the collapse parameter. And that's a table. The analysis has been done again by Adler some years ago. The first columns, so you have the 4 different structures in the universe. The first columns gives the bound in terms of orders of magnitude with respect to the GRW value for lambda, the second column with respect to Adler's value for lambda. There is just a difference of 8, 9 among the two. And you see that, again, these bounds are very weak with respect to the GRW value, but they are quite meaningful, but still compatible with respect to Adler's value. And so here you have a summary of all known upper bounds. So the -2 refers to the fact that spontaneous photon emission with the original CSL model excludes Adler's idea, but one should take, again, these bounds with some care. Most of them, as indicated in the slide, are very sensitive to the type of collapse model you are considering. By changing the model, you can radically change the prediction and therefore with the comparison with experimental data. The idea, which has not been proven, but I mean, in a rigorous way, but somehow it's a feeling that probably it's true, is that only it's matter wave interferometry that is resistant against changing the type of model. So that represents a real test of collapse models and not of the specific model. So at the end of the day, it's matter wave interferometry that will represent the most crucial test of these models, which at the end of the day is not surprising because this is a direct way of testing the superposition principle, which is what is violated by these models. Okay, I want just to test, to mention two recent results. You know that there are naturally oscillating quantum systems like neutrinos, neutral kaons, chiral molecules. This oscillation is the direct consequence of the superposition principle of quantum linearity. So collapse models which violate the superposition principle have something to say about that, and they predict a different oscillatory behavior. And then we started doing some calculation. Of course, the difference with respect to the standard quantum prediction is very tiny because the mass is very small. Nevertheless, with this system, you can play around, you can do entanglement, you can work in very clean environments. So there is the hope that something interesting, some interesting bounds can come out of that. And Beatrix, who's here, is also working in this. Also in this direction. And then why not performing experiments in the frequency domain? Collapse models change the spectrum of atoms and molecules. They add a Lamb shift and a broadening to the spectrum. And we did a calculation, and hopefully, I mean, that's at least the conclusion of the paper is that with the present-day spectroscopy technology, you can hope to test these effects. They are very tiny, but spectroscopic experiments can also be very precise, and so that works in their favor. So I just publicized this recent result. And then I also want to mention that interest is increasing in the possibility of testing collapse effects in the early in the inflationary model for the universe, and there are more and more groups which are interested in that you have a list of the recent papers. The story is very simple. If the universe doesn't evolve according to the usual standard model, but according to the collapse version of it, then you modify the history of the universe in a very tiny way, but the universe is big, had a lot of time to evolve, so possibly you can see the consequences. And I mean, it's very difficult to put collapses in the cosmological setting. People started working on that and got some preliminary results.